All right, welcome back. A lot of repetition here, and repetition is the mother of mastery, and practice leads to progress. And the last two videos, which I recorded a day or two ago, it would have been Wednesday night. It's now Friday morning. But rock and roll, you get done what you can get done, you do what you can do, and you keep pushing it forward, and you work into the night, and you work on the weekends to make it happen. And lucky for you, fortunate, this is a semester where I'm recording the statistics lectures, and so it's taken a lot of work on my part, but it's also keeping all of these current and fresh and with my most up-to-date understanding of statistics. So I'm explaining it better than I've ever explained it, and you're getting to benefit from that. So am I, but it takes a lot of work. So weekends, evenings, here we go. In the last two videos, what we did is we calculated the expected value mean for random variables, and with the expected value, the mean for a random variable, we saw that the formula was, there's the variance, it was this, where for an example here, we have like, here are the random variables, here's the function and the probability when that variable gets put into this function of 1 sale a day or 2 sales a day or 3 sales a day. So we take the random variable, we multiply it by the probability, we get that value, and we do that all the way here. We get all those values multiplying across. That's what this formula here says. Take the random variable, multiply it by the probability that's created by sticking that random variable into that function, and then we get that result and we add them all up, which is what that sigma notation there is. And so that's how we get the expected value or the mean. And you've already heard my thoughts on statistics being confusing. Why didn't they just keep calling it the mean? But here they call it the expected value, which kind of makes sense. It's the value that's expected every day. Is you're going to do like 1.5 car sales every day. And then we also looked at how do you do, and so we had this video here, how do you do the variance and standard deviation for a random variable. And with the variance and standard deviation, the formula was this, and so we calculate the variance, and then we take the square root of that to get the standard deviation. And to calculate the variance, we're looking to see how much each data point varies from the mean. And so here is the notation mu or mu. How many other classes have you had where the professor just randomly moos? So here is the symbol, the Greek letter mu, and that is the representation of the mean for a population, and if it's for a sample, it'd be x bar. So we take each data point and subtract it from subtract the mean from it. Subtract the mean. We take each data point, subtract the mean, and then we square it, and then we add all that, and then we multiply it by the probability for that data point, and then we add all those up. And so what that looks like here is we have each data point, and we know that our expected value, our mean is 1.5. So each data point minus the mean gives us this. And then we square it, and then we multiply it by the probability. So 2.25 times 0.18 is 0.4050. And then we add all those up. We get 1.25 as our variance. So that's how much things could vary based upon our variance. That's a measure of the amount things differ. Each data point differs from the mean. But then the standard deviation brings that back down to the scale of our data, because we take the square root of the variance. Because here we squared everything, which took everything up from the level of our data, which this is the level of our data is 1 through 5, 0 through 5. And when we square it, it's kind of taking things up, doubling it. But when we take the square root, it brings it back down. So this is like a measure of variance. Variance is a measure of dispersion, but it's at a scaled level. When we take the square root, it brings it back down to the level of our data, and the scale of our data. And the scale of our data is 0 through 5. And the standard deviation, the amount we could expect sales to deviate, the standard for the deviation would be 1.18 cars a day. So our expected value, our mean, is we're going to sell 1.5 cars a day. And the amount, the standard deviation, one standard deviation, right, which is according to Chebyshev's theorem, or according to the 99.8, 95, 88.7 rule, whatever that's called. What is that 99.7, 99.7, 95, 88 rule called, and what were the numbers? Because I know I am I am getting them wrong there. And so it's going to remind us here that, you know, like 88% of our data or something like that is found within, it's 68% of our data. So 68% of our data falls within one standard deviation. And that empirical rule is for normal distribution. And we could say, remind me about Chebyshev's theorem and how much data is within one, 2, and 3 standard deviations. And so now we're going to see Chebyshev's theorem here. And so within one standard deviation, that's where 68% of our data is when our data is normally distributive. That's called the empirical rule. That's the phrase I was looking for. And then here we have Chebyshev's theorem, which says that, and I'm just looking for 1, 2, and 3 within one standard deviation. Chebyshev's theorem is 1 minus 1 over k squared. And so Chebyshev's theorem does not provide a useful result here because the formula gives 0. And then within 2 standard deviations, 75%, and within 3 standard deviations, 88.89%. And so I guess Chebyshev's doesn't tell us at 1. That's kind of new information for me. I'm learning this too. All right, so that's it's a little bit of a review, and you can see here that our standard deviation is 1.18 cars. So if this data is normally distributed according to the empirical rule, we could say 68% of our data is going to be, the expected value be 1.5, and 68% of our data will fall in 1.118 standard deviations. So that will be between 0.39 and 2.61 cars being sold each day. That'll be 68% of our data, or 68% of the time. We're going to sell between I don't know, what was that? 0.39 and 2.61 cars each day, 68% of the time. Kind of interesting to connect all those dots. I don't know if I should just leave this video as a review. I think I will, and then we'll jump to the next. I got to do reviews when I come back in just because of what were we talking about. So I'll leave it as a review, and the next one we're going to jump in and talk about bivariate distributions. See you in the next video.